Alright, hello everybody. Today I'm going to be talking about networks and quantum computing. I've really been fascinated with this topic for quite some time, so I was really excited when I found a couple of articles that kind of connected networks and quantum computing. So let's go ahead and dive right in. First, let's talk about some technological advancements. Computing has continuously evolved to be smaller and more powerful. We see that in the difference between the very old giant disks that took up an entire room to store, 1, maybe 2 megabytes worth of data, to our now brand new SD cards, which contain 64 gigs of data, which is really, really incredible. However, as we keep evolving our technology, we're eventually going to hit some physical limits. Transistors at this time are only a couple of atoms wide, and we really can't get too much smaller due to electrons moving through closed transistors through a process called quantum tunneling. Quantum tunneling has caused a lot of headaches for scientists for a very long amount of time. So where do we go from here? That's the big question. And so scientists thought, we have quantum tunneling, let's use it to our advantage. Quantum computing. Very, very awesome stuff, guys. So quantum mechanics have existed for over 100 years, and they depict a physics that don't exactly apply to the bigger world and to traditional physics. So things get very complicated. But in short, what is quantum computing? All right, is it faster? Is it more efficient? Is it even possible? So we're going to go ahead and expand on a couple of these ideas throughout this video. Great. So what is quantum computing? All right, traditionally, computers have operated on bits, either 0 and 1, which we all should know by now. Even people not in our field know this at this point. We consider that to be binary, and with more and more bits, we can form more complicated statements. Look at our ASCII table, for instance. We can describe characters using lots and lots of bits. However, we have a physical limit. Again, quantum computing replaces bits with photons. So instead of little bits, we now have photons, which we call qubits, and they're also binary, which is a great thing. And it derives its value from the vertical or horizontal polarization of the photon. This is very, very important because that photon can be in any proportion of both 1 and 0 at the same time. All right, and this right here is a picture of quantum tunneling. In the classical picture, you can see the energy barrier. This is supposed to represent a transistor, would stop the stop electrical current from passing through. However, in the quantum picture, we really see that it can kind of phase right through it and move over to the other side regardless of that barrier, and that's a really big problem. This picture was taken courtesy of I can't exactly say his name. I'll leave a link to his video. However, it's really awesome and really explains quantum computing in a simple form. But this picture right here, the blue one is a photon, and as you can see, the waves following it are both horizontal and vertical. So that was just to give you guys kind of a visual representation of what I mean when I say it can be both. Okay? And this topic of how a photon can be both vertical and horizontal at the same time via polarization is called superposition. Now, traditional computing with 4 bits, obviously that gives us 16 different combinations, and we can use one of the 16 different states at a time. However, with quantum computing with 4 qubits, we have 16 states simultaneously, because each qubit is both 0 and 1 at the same time, which is kind of crazy. We can exist 16 states simultaneously. And that's really one of the biggest advantages of quantum computing. Of course, it wouldn't be my own presentation if I didn't throw in a couple of jokes. All quantum computing jokes are basically going to be about being simultaneously there and not, just like this one. Hope you enjoy it. So next we're going to talk about entanglement. Qubits can be in any proportion of the two states simultaneously, like I mentioned earlier, but big question is, do they affect each other? And in reality, the answer is yes. Qubits, by observing one, we could tell properties of another qubit if they're entangled. And we can do this for a system of qubits, and even more so, the distance between the qubits do not matter. All right, so it's a very, very awesome property. Now, advantages of this: it's faster. It is. It's more efficient, especially in database searching. Traditionally, especially in SQL databases, large SQL databases, sometimes we have to check every data entry just to find what we are looking for. However, with quantum computing, it takes a square root of the amount of time to search a database, which is incredible. Simulations now become even more so popular and probable now. We can simulate different strings of proteins, different drug models, chemical models. Simulations really can take off and revolutionize the world, so to speak. But more so, we can also simulate quantum physics. Traditional computing cannot handle simulations of quantum computing, or quantum mechanics even. But with quantum computing, simulations are way easier. Again, calculations become much faster, and we can revolutionize the world. All right. So, this is, again, just another fun joke, computing joke. So I hope you guys like these. I tend to, so yeah. But anyway, moving on. We have to ask ourselves the bigger question now. I've just talked up quantum computing quite a bit. So here's the big question. What could possibly go wrong? All right. And the big answer is security. Security is a very, very big problem with the introduction of quantum computing. And here's why. So we use public key cryptography nowadays. And people are asking, is quantum computing advancing too fast? All right, there is an in-between period where we have quantum computers, but no security tools there to defend against it. And the bigger problem is that people are worried that attacks are now going to be made against the public key cryptography and breaking in. And so this is how public key cryptography works. You basically give a public key to the sender. He goes ahead and uses that public key to encrypt his text, and he gives you the text, to which you use a private key to decipher. Now, we know public key cryptography can be cracked. However, with traditional computing, that would take years and years of trial and error. So it's really not efficient at all. With network security, security tools take time to develop. The big question is that with quantum computing, we're no longer just breaking, a code. Just recently there was some malware found for Linux. It was brand new. It was discovered in 2015. And with malware, we isolate it, we remove it, and we create a patch for this. The problem with quantum computing and network security is we're not just breaking in. We are now breaking the philosophy or the base of public key cryptography and cryptography in general. Everything that we've built cryptography around is now going to be broken. So I took this quote. It's a very powerful quote. When cryptographic foundations upon which a cyber system is built are the fundamentally broken, unless a failover replacement, which generally takes years to develop, is in place, the system will crumble with no quick fixes. And that's what everybody is absolutely terrified for. It's almost a panic. And With one of the articles, it was stated that there's a 1 in 7 chance that the key cryptography tools will be broken in a decade, and even more so by 2031. Quantum computing could render militaries, businesses, and communications immobile, especially if they are introduced into the network without any form of security. So, any bigger question, what do we do about this? Should we ban cryptography? Should we ban quantum computing? I say no, of course, because it could revolutionize the world as well. However, scientists saw this kind of coming, and they started working on a few different solutions. All right, and these solutions have one of two different goals. So the first goal is to create quantum-safe cryptography tools that can run on traditional computers. That way, once we have the introduction of quantum computers into the network, traditional computers don't have to be upgraded immediately, and they can still be safe. Or really, create an unhackable internet. And scientists are already working on that, and it's kind of in the process right now. So what are they doing? Well, first off, they're using a 1930s radio technique to make an unhackable internet. Using a modified laser equipped with quantum light, scientists shoot this through a gallium arsenide chip, and it separates the signals. However, there's one problem with this. Quantum light is much weaker than classical light, and in order to stipulate it, they use this 1930s radio tech that we use almost every day in noise-canceling headphones. Is we send an opposing signal to cancel out the classical light, which emanates the quantum light even more so. All right, so this is a visual representation. The blue light is quantum light, and the red light is classical light, and this is a gallium arsenide chip. And as the light passes through, it filters out the classical light and it holds onto the quantum signal. All right. Why is this more secure, do you think? Well, for one, this is way more secure because along with quantum computing, I mentioned earlier that qubits can emanate in both states simultaneously. Well, it isn't until we try to run them through a filter that they have to decide to be 1 or 0. Similarly, through this method over here, if the light is ever intercepted, it has to choose to be 1 or 0 and can crumble, destroying the data, making it a lot safer. So I hope I haven't scared you all with quantum computing. These are my credits. I will post this slideshow on the web, so if you guys want to check out my articles or the video by Kurzgesagt, I hope that's how you say it. He's really awesome. Check him out on YouTube. And that is it. Thank you very much.